So the last talk of this session will be Anuj Jain. I hope I pronounced that correctly. And he will talk to us about some path and walk problems in temporal graphs. Go ahead.
Okay. Hi, everybody. Welcome to my talk on path and walk problems in the temporal graphs. I'm Anuj Jain, and this is joint work with Professor Sartaj Sahni from University of Florida. Okay, so just to, quick introduction of temporal graphs. These are graphs that change over time. Vertices and edges may appear or disappear, or their properties might change. Formally, they can be defined as a sequence of static graphs from G1 through GL, for example. Each GI represents a static graph at time instant I. Alternatively, if time is considered to be continuous, then GI represents a static graph over a time interval Ti to Ti plus 1. So some popular representations of the static graph. Here I show contact sequence temporal graph versus interval temporal graph. So the one on the left-hand side is a contact sequence temporal graph. This is kind of a special case of the interval temporal graph when the time is discrete. And as we can see that if the duration or the interval durations for availability of an edge between two vertices is large, then the number of edges in the contact sequence can be very large. They can explode. And we also show that some problems are NP hard in the interval temporal representations, but are polynomial in contact sequence just because the size of the input is very large. There are many practical applications of temporal graphs, as everyone here is already aware. So just to give a few examples, they can be used for analyzing information and information spread in social networks, for modeling disease spread for pandemics or epidemics. They could be used to find optimal paths in ad hoc wireless networks, or for optimal flight routes, or even for optimal travel paths in road networks, because road networks keep changing over time as the traffic patterns change and new streets appear and so on. So we'll start with interval temporal graphs. This is I present several algorithms in this talk, and for interval temporal graph, this is the data structure we use. This is just a array adjacency list where all the vertices are in an array, and for every vertex, we have an array of all the neighbors to that vertex, and for every neighbor, we have an array of all the intervals presence between the vertex and its neighbor, and every interval can have a different travel time. Okay, just to give a quick definition of optimal paths in temporal graphs, there can be many different ways to define an optimal path. So some of the ways are like a foremost path, which is a path that arrives earliest at the destination vertex. Min hop path is a path that would arrive with a minimum number of hops at the destination vertex, and shortest path would be the one that arrives with a minimum travel time. So again, to give an example with a picture, so a foremost path in this temporal graph on the right-hand side would be from between S and C, would be starting from S to A, reaching A at time 1, and then departing A at time 1 to reach B at time 2, and then departing from B at the next available interval 3 to reach C at time 4. Whereas a min-hop path would be departing from S to B and then to C, which reaches C in 2 hops, but arrives at time 6. So we have proposed algorithms for foremost and min-hop paths in interval temporal graphs. Our algorithms handle variable times per interval, as opposed to an algorithm from Schwein, who also proposed algorithms for interval temporal graph. We use a slightly different data structure than the Schwein's. And our foremost algorithm is just a natural extension of Schwein's algorithm, because we include variable travel times per interval, whereas they require the travel time to be the same across all intervals on a given connection. Then our min-hop algorithm is a fundamentally different algorithm. For benchmarking, We benchmarked against Schwann's algorithm. We had to make some improvements to their algorithm to be able to benchmark. And then we benchmarked against Wu's algorithm as well. They define their algorithms on contact sequence model. So, okay, so the data sets that we used for comparison of our foremost and min-hop algorithms are called Koblenz data sets. These are the same data sets that were used by Schwann and Wu in their benchmarking. What this table shows is that the number of, so on the right-hand side is the activity on each graph. The activity is the ratio of the contact sequence edges to the static edges in the underlying graph. And as we can see that the activity varies from 1 to 3.67, and which is kind of low. And and then the number of contact sequence edges go as high as 572 million. And then because the activity in the Koblenz datasets is low, we also developed some synthetic graphs. These are developed from the static social network graphs from YouTube, Flickr, LiveJournal. And we just added temporal parameters to every edge of these graphs. The parameters are basically the number of intervals of travel on that edge and the duration of each of those intervals, and then the travel time for that interval. And these are just normal distribution around these mean values. And as we can see that the edge activity is much higher for these synthetic graphs. Now for the comparison of the results on the foremost against the Wu's on the Koblenz datasets. Now again, Koblenz datasets were originally contact sequence models, so they prefer, or they are, they favor the contact sequence algorithms. So we see that in the foremost paths, we do better than them on some of the data sets, but they do better than us on some others. Whereas when we look at the synthetic data sets, we do better than the Wu's algorithm on all the data sets because the activity factor is much higher. And here, as you can see that in one of the Koblenz data sets, we do 1800 times better. That is just because the data set is highly disconnected and their algorithm doesn't discover until much later that the data set is disconnected, but ours does. And then doing the min-hop comparisons against the Wu's data sets or the Wu's algorithms, we see that on the Koblenz data sets, we do better on almost all of them except maybe 2 of the data sets. And then comparing against the Schwann's algorithm also on the Koblenz data sets, we do better on all the data sets, getting a speed up of up to 31,400. Again, because we discover that the graph is highly disconnected. And then finally, the min-hop comparisons against the Wu's algorithm on the synthetic data sets, and we get a speed up of up to 22 or 23. Okay. So after that, we considered some problems with dual optimization criteria, such that now we have a primary criteria and a secondary criteria. So in these problems, the primary criteria is the foremost paths, and then the secondary is the MHF. So secondary is the number of hops. So we want to find all the foremost paths, but not all of them. We just want to find the foremost path that reaches there in the minimum number of hops. And then similarly, we develop a polynomial time algorithm for the MHF paths. And then there is a MWF walk problem. And we proved that this problem is NP hard for the interval temporal graph, but polynomial for the contact sequence graph. And we develop a pseudo polynomial algorithm for the MWF walks. Again, these are the foremost walks that arrive at the destination with minimum wait time across the entire walk. And then finally, the min cost foremost. This is also NP hard on the interval temporal graphs. And the algorithm would be very similar to the MWF algorithm. So this is an example of the MHF paths in the interval temporal graphs. As we can see, traveling from vertex A to D, we have a path that goes from A to C, reaches C at time 7, and then departs C at 7 to reach D at 8. And another path that goes through B, C, and D. Both the paths are foremost paths as they arrive at the same time at D, which is time 8, whereas the first one goes through a lesser number of hops, and that is the only MHF path in this graph. Just to give a little bit of insight into how the MHF algorithm works. This is a hop by hop algorithm that explores vertices in every hop and updates the paths if it finds a better path. So for example, let's say the starting vertex was vertex S, and we wanted to find MHF paths to all the other vertices in the graph. In hop 1, we explore all the one hop neighbors of S, which is A, B, and C. We can reach A at time 1, B at time 5, and C at time 10. And then in the next hop, we try to extend all the one hop paths discovered. So in the second hop, we say that the one hop path was A, trying to extend A. I can extend it because I reach A at time 1. There is an outgoing interval available at time 1. So I reach B at time 2. Now I see what was the earlier path to B, which was a one hop path that reached at B. So this one reaches earlier, so I update the paths to B. And now I have a two hop path to B. Similarly, the other one hop path I had was from S to B. I try to extend that, and I see I can extend it to C. And I reach C at time 5 plus 1, 6, which is better than the earlier arrival time of 10. So I update that path to vertex 6. And then the other one hop path I had was S to C, which reached C at time 10, but there is no outgoing time available at 10. So I can't extend it. In the third hop, I try to extend the two hop paths reached so far. So they are SAB and SBC. Now trying to extend SAB, I reached B at time 2, and I see there is an outgoing interval available after 2 at 3. So I find a three hop path to C, which reaches C at time 4. The earlier two hop path I had at C reached there at time 6. So I got a better arrival time. So I update the path to C, and I get a three hop path to C as SABC. The two hop path I had to C, which was from SBC, reached C at time 6, but I don't have any outgoing path available after 6. So at or after 6, so I cannot extend that. And then finally, trying to extend the three hop paths, I only got one three hop path SABC. That one I can extend because that arrives at C at time 4. There is an outgoing path available at 4, and therefore I discover a new vertex D, and where I can reach at time 5. Now all the vertices have been reached and the algorithm terminates. Okay, again, MWF walks, I would not go into the details, but just to give an example of what an MWF walk does. So first of all, this is an NP-hard problem on interval temporal graph, as stated earlier. So if we were to start from S and consider consider destination as B, then one way to get there would be to depart S at time 2, reach A at time 3, and then wait here for the next opportunity to depart at 13 and reach B at 17. However, an alternate, so one thing to consider is that there is no waiting time at the start vertex or the destination vertex. There would be waiting times at the intermediate vertices. So what I could have done is, instead of departing at 2, I could have departed at 3 because there is a departure available at 3. And I would reach A at 4. Then from A, I could depart at 4 to reach C at 6. From C, departing at 6, reaching D at 7. Going back to A, departing at 7, which is an available departure. Reaching A as 13, and then departing from A at 13 to reach B at 17. So this goes through a cycle, but it reaches B at the same time as the earlier one, but has a 0 wait time through the entire walk. And therefore, this would be the min weight foremost walk. Okay, so now I want to introduce that there was an algorithm proposed by Bentert et al. In 2020. This is a linear combination algorithm where they find optimal walks that minimize the linear combination of various criteria in the contact sequence graphs. So for example, they could minimize arrival time multiplied by a coefficient plus the waiting time multiplied weight and so on. So what we could do is we could choose coefficients for this linear combination such that we can find the min-hop, the MHF and the MWF walks using the Bentert's algorithm as well. So what we did is we benchmarked our MHF and MWF algorithms on the interval temporal graphs against Bentert's algorithm on the CSGs, or the contact sequence graph, using this formulation. And for some data sets, their program could not run because it ran out of memory. And also, I want to point out that when our algorithm runs on the interval temporal graphs, we model the CSGs with 0 duration interval. So the start and the end time of the interval is the same, which is an overhead for representing an interval temporal graph. So comparing against Bentert's on the Koblenz data sets, we observed that we do better on all the data sets and go as high as 207 on this delicious data set. Because this is the contact sequence data sets. But when we go to the synthetic data sets that I presented earlier, we do as much as 679 times faster than the Bentert's algorithm on that. And on the MWF, similarly, just measuring on the Koblenz data sets, we get a speed up of up to 23.3 on the Enron data set. It looks like, so on the 2 of the data sets, Bentert's algorithm performs faster, or 3 of them actually. So, just to describe a little bit more, all the optimization criteria considered by Bentert are the arrival time that we have already looked at, which is the arrival time at the last vertex in the walk. The hop count, which is the number of hops that the walk goes through. The start time, because some problems require the latest departure time from the start vertex. And then there is the travel duration, which is the arrival at the final vertex minus the departure from the starting vertex. Then we have the travel time, which is the sum of the travel time on every edge along the walk. Then we have the waiting time, which is the sum of the wait times at every vertex. And like I said earlier, there can be only weight on the intermediate vertices. So there is no weight on the starting vertex or the ending vertex. So it goes from 2 through k minus 1. Then there is a cost criteria, which is the sum of the cost on every edge, if there was a cost assigned to the edge. And then there is a walk probability, which would be a product of the probability of every edge. But this can be modeled as also the cost criteria, where cost would be the negative log of the probabilities on every edge. And just to define the linear combination problem, what that is that it is minimizing the linear combination of all of these criteria, and the coefficient for each of the criteria is taken as an input from the user. Right. And additionally, we have a min weight and max weight constraint that can be applied to every vertex. So in other words, at every vertex, I have to stay for a minimum of a duration, which is called alpha V, and the maximum duration that I'm allowed to wait on a vertex is beta V. So these are the 2 equations that give that min and max weight constraints. So we also propose a new algorithm to minimize that linear combination with all those criteria described above. And the linear combination of all these criteria and with the waiting time constraints for the contact sequence graphs this time However, our algorithms allows only graphs with no zero duration cycle. That means that there cannot be a cycle in the contact sequence graph such that every edge on the cycle has a zero travel time. So when we benchmark our algorithm for this linear combination against Bentert's algorithm, these are the results. So we perform better than Bentert's on every data set with the minimum speed up obtained on this YouTube growth data set of 5.5. But we get a speed up of up to 77 on this WikiConf data set over the Bentert's algorithm. Our algorithm is based on a TRG data structure that I don't describe here, but this is a time respecting graph. And this is an extension of the TRG data structure proposed by these authors. Okay, so finally, to summarize the results of the path and walk problems, we demonstrated that several problems are NP-hard in interval temporal graphs, but polynomial in contact sequence graphs. That the foremost path algorithm, when benchmarked against Wu's algorithm, which is, which from whatever I studied was the best known for the CSTs, we experimentally shown to be faster by up to a factor of 1800. On the min-hop paths algorithm, experimentally showed that our algorithm is up to 6,700 times faster than the Wu's algorithm. On the MHF, we experimentally showed to be 679 times faster than the Bentert's algorithm. And then the pseudo-polynomial MWF algorithm that we proposed, it is experimentally shown to be 23 times faster than Bentert's. And the linear combination algorithm, finally, which is also on the contact sequence graph. So all the other algorithms we proposed were on interval temporal graphs. Then the final one, the linear combination, is on the contact sequence graph and shown to be 77 times faster than Bentert's. And all the algorithms and results I shared here are being published in these papers. The last one is a 2023 conference, which is happening right now. But all of them have already been published in the past years. Okay, that's all I had.
Thank you. Are there any questions? Maybe online? If there are not, I have a little curiosity. So you said that there was a bug in Schwann's algorithm for, what was it, min-hop?
Let's see.
Yes, for min-hop.
Yes, it was in the min-hop. That's right, yeah.
What bug was this?
Okay, so if I remember it right, I think the problem in the algorithm as they published in their paper was that, they were trying to extend the paths at every hop. However, what ended up happening is that the way they had described the algorithm, because they didn't give an implementation, they just had the algorithm description, and the way they had described the algorithm, when they extend a path, so let's say they extend from hop 2 to hop 3, and then they are supposed to extend the 3 hop paths. But what they ended up doing is that in the same hop, they updated the path to the new vertex. And then in the next hop, before they move on to the next hop, they start using that path. So they end up ignoring what they got from the previous hop. I don't remember it exactly, but I can send you the details later, which we had described in our paper as well.
Okay. Was it easy to fix?
Yes, it was fairly easy to fix, yes. Okay. So it may just have been an oversight, I don't know. But then we also improved their algorithm because they had some inefficiencies where they were redoing a lot of work. And that was also easy to fix. So that is why we just improved that before we did the benchmarking with our algorithm. Okay, I think we can clap again. Thank you.